Okay, we're live. And this is working well enough. A little bit cut off. Okay, so today, after we get through the what? Okay, I have no keyboard. There we go. Okay, so today, after we get through the obligatory disclosure that I'm a Columbia employee, Columbia gets a lot of money to develop STAN, co-founder of STAN Group. We get little money to help businesses use STAN according to Columbia University policy. Those two things together imply have to disclose things like that in presentations such as this. So what are we going to be talking about today? Well, first, there's a review session on Friday. Actually, two of them, but they're going to be the same. One will start at 4:30. One will start at 5:15. They'll both be in IAB 270B, where they've been before. That conference room down by my office. We'll mostly be talking about the process of doing a Bayesian analysis using RSTAN-ARM and V Rms, which we're going to start talking about today. So the V Rms package primarily involves the V Rm function, which we're going to start learning about, and that is going to get us one step closer to using the STAN language directly, although we won't actually get to that this week. Okay. So I put this up before, something like this. Just the workflow of using STAN if you're doing this via R. So someone needs to write a STAN program in a text file that ends with .stan. This has somewhat R-like syntax and defines the posterior kernel that you want to get draws from in log units. And that's going to get translated to C++, compiled into a binary executable. It requires the C++ compiler to not only be installed, but sufficiently recent to do all the auto differentiation and stuff itself. So we're still not going to be writing these programs in the STAN language ourselves until next week when we start that. The RSTAN-ARM package that you've been using before comes with STAN programs that are already written. In fact, they're written by hand. I've done some of them. Jonah Gabri's done some of them. Imad's done one of them, working on another one now. So basically, someone who understands STAN has to write those STAN programs in advance, and then they come with the package. And if you're installing the RSTAN-ARM package from CRAN on Windows or on Mac, then the C++ compiled process happens on the CRAN servers if everything goes well. And thus, when you download it, you already have the binary C++ programs included. What VRMS package, which we're going to be talking about this week, does something a little bit differently. It requires the C++ compiler to be installed on your machine, and what it does is it inputs our syntax with a variety of options, and it generates the STAN file on the fly. And so it, then it generates a valid STAN file that gets parsed into C++. The C++ gets compiled into a binary, and then it runs. And so this, when you do it yourself, you'll see it takes like 30 seconds or so to get going. That's because it's compiling this STAN program that was generated by the R syntax that you provide. But because the STAN files are generated on the fly, it's possible for the VRM function in the VRMS package to generate many more types of regression models that are included than would be included in RSTAN-ARM, because the ones that we do in RSTAN-ARM, it takes us a long time to write those by hand and to make sure they work under the largest possible number of circumstances, choose priors, etc. the stand models that are generated by VRMS, they're basically auto-generated. So you get valid stand code in a stand program that will run most of the time, but there's no human who's sort of checked that it's optimal or tested it or anything like that. So you're a little bit more on your own. Nevertheless, the auto-generated stand code that VRM generates is a lot better than what a lot of humans would do themselves, particularly if they're not that experienced with stand. Anyway, that all happens. It executes the binary from R. The BRM function in the BRMS package does like this in the first step one all concurrently, and then you get back results, and at that point it's very similar to having done stuff with RStanArm. The person who wrote the BRMS package, Paul Christian Bergner, has made BRMS largely compatible with RStanArm in terms of the function names and the concepts and so forth, argument names. So a lot of that is going to seem very familiar when you get to the part of diagnosing and analyzing the resulting samples from the posterior distribution. So in a nutshell, BRMS dramatically expands the set of regression models that you can estimate without you having to write or necessarily look at the stand code that defines that model. Now, you can look at that stand code, and if you want to like edit it, that's a good template to start with. The stand code that gets generated by BRMS is a lot simpler and a lot more readable than the stand code in the RStanArm package. But basically with BRMS, you can estimate, I would say 80% of the models that you could estimate in Stata, but use stand to estimate them, so you get posterior distributions of all this stuff. So you can do a lot, and maybe many people would never need to go beyond what BRMS offers. Now, many people are not that ambitious, so I don't know that necessarily means that you should not go beyond VRMS. And in fact, next week we will. But, if you're doing this for research, particularly if you just need something, relatively quickly, VRMS will likely have the functionality that you need. Questions about that? No? Okay. So the workflow is specific to VRMS, and actually, from the human's perspective, there's fewer steps than this, because it's basically all driven by the VRM function. But the user, that being you, passes all model information to VRM, and what this amounts to is specifying a formula, a data frame, a family, to define the likelihood, some stuff about the priors, various other options, pass that to the BRM function. The BRM function internally calls functions make underscore stand code and make underscore stand data. Make stand code generates the stand code that's implied by the R syntax you specified in the first step, and make stand data processes the data frame that you supplied it, and so the data is in the form that the stand program expects. You don't have to do that explicitly, although it is possible to do so yourself. But the BRM function calls make stand code and make stand data internally. All the result of that is then passed to the RStan package, which that part of it is very similar to how RStanArm hands off to Stan, and then estimates the model. Like I said, in the case of VRMS, there's an additional step where the Stan code that was generated in the second step is translated into C++ and compiled before the actual model fitting part doesn't stand. Then after Stan is finished, you have draws from the posterior distribution. It's post-processed a good bit by the BRMS function to make it easier for you to interpret and keep track of like what parameter is what. RStanArm has a similar step, and it's tedious to code. This is mostly because like when you get the results back from R, in general, it has no idea what the Stan program was doing or specifying the model and whatnot. So when you get raw Stan output, it's just like theta1, theta2, theta3, all this. What BRMS and RStanArm do is an additional step where instead of having like theta1, theta2, theta3, you have like age, income, etc. These are the coefficients on those variables, and it'll substitute the names to get those right. And then you get back a list. It's a similar sort of thing to the list that the functions in RStanArm produces. You can coerce it to a matrix or a data frame. You can pass it to Shiny Stan. You can do posterior predictive checks with it. Of course, you can look at posterior means and stuff like that. But you know, at that point, you can pretty much do anything that you can do with one of the things that RStanArm produces. All right. So as far as the person is concerned, the most important steps are the first and the last, where you define using R syntax what posterior distribution you're trying to obtain draws from. And then VRMS takes your R syntax, generates equivalent Stan syntax. RStan takes the Stan syntax, generates equivalent C++ code. C++ code gets compiled, executed once you pass, or once the data is passed to it. You get, at that point, quick draws usually from the posterior distribution, and then you analyze it in the ways that we've already been learning about. So what we're going to mostly focus on today and also on Thursday is how to sort of specify the R syntax in the BRM function to define the Stan model that you're trying to estimate, or the model that you're trying to estimate with Stan. Got it? Okay. So the RStanArm package has a variety of model fitting functions that are preceded by Stan underscore. So you have Stan underscore LM, Stan underscore GLM, Stan underscore GLMER, some other ones, etc. that the sort of name of that function takes an existing function that's, you know, pretty popular but only has frequentist estimation methods, prepend Stan to that, and then, you know, specifies some additional arguments about priors and stuff, and estimates it with Stan rather than frequentist methods. So there's like 5 or 6 different model fitting functions in the RStanArm package. And if you sort of understand what GLM does, then you sort of automatically understand what Stan GLM does. You know, it's just Bayesian. The BRMS package has basically one function for fitting all the models that it knows how to generate Stan code to fit. Consequently, the arguments to the BRM function, there are a lot of them. The first 3 or first 4 maybe are the most important. The formula, which is specified in a similar way to a lot of other R functions, but, you know, no function in particular. A data frame, that's the second argument. A family, so this is, you know, first 3 of these are very similar to how RStanArm does them for, you know, Stan GLM, Stan GLMER, etc. There's an argument where you can specify your prior. That is a little bit different in VRMS. We'll get to that. And then there's a bunch of other arguments, like 20 different arguments or something like that, that are mostly specific to particular models, not all of which we are going to be talking about today. So some of these, once you get down to like fit and its chains, these are all arguments that are just passed to RStan. So the ones above this actually pertain to the model that you're specifying. The rest of this toward the bottom half here, it's just additional arguments that all have defaults for how the Hamiltonian Monte Carlo via nuts proceed. So, inits are random. You're going to do 4 chains by default, 2,000 iterations by default. Half of those are thrown away as warm up. Use the option that you set for MC cores for how many cores to use. Some other stuff like a seed, etc. That when we get to Stan next week, you'll see these are the same arguments that are being accepted by the Stan and the sampling function. So today we're mostly going to concentrate on the first 4. The first 3 you pretty much have to specify. The priors you more or less have to specify, but the other ones here are optional for the most part, although you may need to specify some of them for particular models. All right, so let's start with the formula argument. So this is largely similar to what we've learned before. The formula is going to have a tilde in the middle of it, and everything to the right of the tilde is going to involve the same syntax as in the Stan underscore glmer function, which we just stole from the syntax of the glmer function in the LME4 package. So that part is going to be consistent. And in most cases, everything to the left of the tilde in the formula is simply going to be the outcome variable. But the BRM function introduces a new syntax into R that starts with like y, and then you have a vertical bar after y, and then you specify some function of another variable that is necessary in some cases. So the fun function could be sens or trunk if you need to specify a model that has censoring or truncation. It could be weights or dispersion or disp. Neither of those should really be used with MCMC, but BRM, just like a lot of the functions in RStan ARM, you can also do optimization. It's just not a good idea. There's an SE possibility to specify for the function. This allows you to specify if you know what the standard errors of the outcome variable are. This is often sort of done in so-called meta-analysis, where you're analyzing the results of a bunch of other studies. Now, in those studies, you don't really know what the standard errors are. You know what the standard errors were estimated to be. But a lot of times when doing this, people just take those standard error estimates as if they were known data. So you can specify models for meta-analysis like that. There's a trials function. This is only used in binomial models. This is a little bit different from Stan GLM. So in Stan GLM, you have to specify a 2-column matrix, the number of successes and the number of failures. Those 2 things add together to be the number of trials for each row in your data frame. However, BRM specifies it a little bit differently. Y would be the number of successes, and then you would say trials is given by some other variable. So you specify the number of successes and the number of trials. The difference between those is the number of failures. But specify any 2 of those and the third. There's also another one called CAT. in which you can specify some categories for ordinal models. We'll talk about an ordinal model toward the end of class today. There may be some others for situations where the outcome is multivariate. So VRM can do a little bit, some like maybe Gaussian models where the outcome is not just a single observation, but rather a vector. Our RStanArm doesn't have anything in that regard yet. Only have model fitting functions for outcomes where the outcome is scalar for each observation. So we're actually not going to get into any of these possibilities today and may not get into them Thursday. I just wanted you to be aware of those in case you need to look more deeply into how to specify one of these models. But for the most part, the formula is pretty much the same as in like Stan GLMER. All right. You can also have these vertical bar constructions to the right of the tilde, but that just means the same thing as it does in LME4. We're allowing stuff to vary by group.
So can you say like norm, then the linear function to the mean, and then sigma in that fund?
No. So the likelihood is specified by these family arguments rather than by saying, you know, there's some like mean and standard deviation to y. So I think these 6 or 7 are the only fun variables that you have to possibly worry about. There may be some others. There may be more things added. Paul adds things at an unbelievably fast rate. So these slides are probably already out of date and I just wrote them this afternoon. But yeah, so there's some additional flexibility in how you specify the left-hand side. So the BRM function also takes a data frame, but that's pretty standard in R. There are lots of family or things that can be passed to the family argument of BRM. Indeed, more than can be passed to the family argument of like Stan underscore GLM or Stan underscore GLMER. But it, you know, the family argument of BRM takes all the families that GLM or Stan GLM can take plus more. So there's a bunch here. Student for specifying that the outcome is distributed, not normal, but student T. And it's going to estimate the number of degrees of freedom of that student T distribution in addition to estimating the scale parameter of a student T distribution. As the degrees of freedom gets large, then the student T distribution converges to the normal distribution, and it'd be like estimating something with Stan underscore GLM. All of these, most of these family arguments take a link function, which maps from the conditional mean to eta in the case of a generalized linear model. Bernoulli, which is just a specialization of binomial, negative binomial, which I think we also did an example of. You can do that in RStanArm as well. It's a generalization of Poisson model, or Poisson is the limiting case of negative binomial that allows overdispersion in the outcome, which is pretty typical in the social sciences. Geometric is a distribution for discrete outcomes. We have not talked about this yet, so I don't want to get into it today, but it's kind of like multinomial, but has different assumptions for the sampling mechanism. Log normal, which is actually just a specialization of Gaussian with a exponential inverse link function. Exponential for estimating models. This often comes up in survival analysis to say the likelihood of the amount of time until something happens has exponential distribution. the same for Weibel and I guess just Weibel. But any of those are two of the more common likelihoods when doing survival analysis, and which is very common in public health and a lot of other fields. You know, exponentially modified Gaussian, beta. So when you're modeling proportions, you can do this in RStan-ARM now, but it's a pretty recent addition. We've got a bunch of hurdle families. These are mixtures of different models. We may talk more about these sorts of things on Thursday, but oftentimes when modeling count data in the social sciences in particular, you'll have a situation in which like there's kind of a reasonable distribution for most of the values, but under that distribution, there's more observed data points turn out to be zero than is you know, predicted by that distribution. So Poisson, you know, zero is in the sample space, but if you have like Poisson with lambda of 10 or so, zero is very unlikely. But in actual social science data, a lot of times we see data with sort of an excessive number of zeros, and then maybe a Poisson more or less applies to all the positive counts. And so we probably will talk about on Thursday hurdle processes, zero inflated processes that are useful for situations like this. Categorical for modeling an outcome that it's just a nominal variable, doesn't have any explicit ordering. And the last four here, we'll talk about some of them toward the end. Those are for modeling outcomes that are ordinal in various ways. And so there's a whole bunch of likelihoods that you can specify. You can also specify them by calling the VRMS family function and passing a string to the family in the link argument to specify one of these things. And so, you know, VRM includes all the families that can be done by the various functions in RStan-ARM, plus a bunch more. So you do have a lot more choices, a lot of different types of models. Wouldn't surprise me if you can do like 1,000 different models or something, or, you know, variations, 1,000 different variations on like a big set of models, just using the BRM package, which just uses Stan to estimate things. All right, so a lot of choices there. The prior argument to BRM is fourth, and this has to be specified by a call to set underscore prior. And the arguments to set underscore prior, there's also about 8 or 9 of those. Most of these take in character strings. So the first argument to prior is a character string specifying what you want the prior distribution to be in the Stan language. So we haven't really learned about the Stan language, but just to like maybe give something away, it has a normal distribution in it. And if you want a normal distribution with a mean of 0 and a standard deviation of 5, you can just put in the character string, quote, normal, parentheses, 0, comma, 5, parentheses, quotation marks. And pretty much what VRM does is it just takes those strings and inserts them into the Stan program that it writes, and then it gets translated to C++, and translated into object code, etc. So you're basically just putting in like words here for those priors. Then you have to specify the class argument, or it has a default of B, but specify the class argument to indicate what parameters this prior pertains to. So by default, that's B, which means regression coefficients. We'll talk more about that in a second, but there's different sorts of parameters that you can have in one of these models. And so you need to have the ability to say, okay, normal 0, 5, what parameter are you talking about? So that goes that way. You can specify the coef argument. This one is going to be optional. So, you know, if you really want to specify one prior distribution for the coefficient on income and another prior distribution for the coefficient on age, you can specify the coef argument to be like income. And then whatever you've specified to the left of that, it's going to pertain to the coefficient, your prior beliefs about the coefficient on income only. If you don't specify the coef argument, then it's going to take this prior and apply it to all of the parameters of that class. So if you just do, you know, set prior normal 0, 5, that's going to put a prior with a mean of 0 and a standard deviation of 5 on each regression coefficient rather than, you know, something for income, something for age. You can do this with multiple calls to set prior where you specify the class and the coef. If you're estimating a multi-level model, you may need to specify the grouping factor that you're referring to. So let's say you have like, you know, different intercepts for each race category or something like that. So then you're going to have to say something about like your prior for the standard deviation on how much the intercept varies from one race to the next. In LPAR, this pertains to nonlinear models. We may talk about that on Thursday. RESP is usually optional, but if you're specifying a model that has multiple outcomes, then you might need to specify what response variable you're referring to its coefficients about. And then LB and UB just specify lower bounds and upper bounds on the parameters. This is quite possible in STAN. It's usually a bad idea for regression coefficients. Obviously, for things like standard deviations, those can't be negative, but you don't have to specify like lower bound equals 0 for standard deviations. BRM knows how to do that for you. But there's some situations in which it's possibly appropriate and more situations in which people do things like this to specify like this coefficient, I know it's like positive, in which case you can specify a lower bound of 0 on those and then specify, you know, a prior argument that's supported over the positive real numbers. So you probably would not want to use a normal distribution if you were saying there's a lower bound of 0, even though STAN will sort of interpret that as what's known as a half normal distribution. So take away the negative part of the density, multiply the positive density by 2, so it integrates to 1 again, etc. But for the most part, you're not really going to be specifying lower bounds and upper bounds that much when you use the VRM function. So aside from the class thing, which we'll talk about more in a second, actually I want to just show this first. So specifying prior beliefs in VRM can be a little bit involved because it estimates so many different models. There's so many different sorts of parameters that can be in any model. It's a bit difficult to convey your prior information. And so Paul has helpfully written a function called get_prior, which takes the first 4 arguments of, you know, BRM and says, okay, if this was my model, what are the default priors for a model like this? And I didn't do it here, but actually if you specify the 4th argument prior, then it's going to override the default with whatever you say, and the output will be like your priors whenever you override them. So you can check that this makes sense. So this is a model we have not talked about, although I'm sure our public health friends would be happy to tell you all about a model like this. So this is a model where we're modeling time. And in public health, this is usually time until the person dies. it has this censoring mechanism because researchers run out of grant money before all the people in their study die. So there's some people who are not dead yet. And those are going to be coded as censored. It just says like their time ran to the end of the study. And so that has to be incorporated. The predictors here are going to be age, sex, whether the person actually has the disease being studied. And we're going to allow the coefficient on age and the intercept to vary from one patient to the next and have some prior on that. We're apparently talking about some sort of a kidney disease, and the likelihood it's using for time is log normal. Probably gamma or exponential or Weibull, more common than log normal, but in this case we're using the log normal likelihood. So it comes out with this information. So the first 9 or so things here are coefficients on the predictors that you've specified in this model here. So the first one doesn't have a name, that's just the intercept. And it's saying that it's not putting a prior, which is to say it's putting an improper uniform prior over the entire real line for all of these. And then we have a coefficient on age. We have a coefficient on the interaction between age and female. The disease is apparently a factor that can take on 3 levels, usually pertaining to the severity of it, but I don't actually know what those mean. Then another intercept pops up. So actually, I don't know what row 1 is, but anyway, there's a prior for the intercept and a prior for the so-called main effect of being female, which you could interpret as the effect for females whose age is 0 with the interaction thing. So you could specify priors on each of these coefficients here, but by default in VRM, it just does improper priors for those. Yes?
What is there interaction between age and sex? No, there's no. Oh, that's
Yeah.
What's the 1 plus each patient thing?
So that's the same as in STAN GLMER and in LME4. We're going to get to that. It's saying, okay, the coefficient on age is going to vary randomly from one patient to the next. We have multiple you observe people over time in a study like this. So that so to just jump into that, there's a prior on the standard deviation of these things. So the standard deviation of how much the intercept varies from one patient to the next. I think this is supposed to like fill down, but they don't write it out every time. Anyway, all of these have a student T distribution with 3 degrees of freedom and a scale of 10 and a location of 0. So as we said before, standard deviations have to be positive. VRM knows that, and it generates STAN code that is consistent with that. And so this student T distribution is really a half student T distribution. It's impossible. It takes away the negative part of the density and folds it over onto the positive part of the real line. So this is a student T distribution accounting for the fact that it has to be positive. By default, it's doing a student T distribution with 3 degrees of freedom. So that's going to have a long tail. Student T with 3 degrees of freedom is sort of the first integer number of degrees of freedom such that the expectation and the variance of the student T distribution are defined. and finite. So that's the reason why it does 3 there. You don't have to do an integer. You could do a real number there. In some models, it's actually going to estimate the degrees of freedom. But in this case, it's just you're specifying your prior beliefs that it's a student T with 3 degrees of freedom and a scale of 10. So this is one of the differences between RStanArm and BRM. In RStanArm, we're going to have a default prior for everything. And those default priors are usually going to be pretty good or applicable to, a lot of the times when someone would call a function like this. With BRM, it's sort of piecing together all these models on the fly from like different parts. It's like Lego of Stan models or something like that. So it's not exactly clear in a lot of situations what would be a good default prior, because it sort of doesn't know in advance what model it is it's constructing. And Stan programs can be so complicated that there's no way to like build a Stan program and then after the fact read the Stan program, apply some AI business to it, and then figure out what good default priors would be. So a lot of these are just kind of pretty conservative guesses. So improper uniform over the whole real line on the coefficients, student T distribution with heavy tails and a big scale on these standard deviations. That also applies to the coefficient on age, which varies from one patient to the next. The log normal distribution has a standard deviation for the errors. That is also going to have this student T3 thing. And then, so this defines a construction where both the intercept and the coefficient on age vary from one to the next. And so you need a 2x2 prior on the correlation matrix after you've specified priors on the standard deviations. And by default, that's going to be one of these LKJs with a shape parameter of 1, which is to say all 2x2 correlation matrices are equally likely a priori. And that's going to constrain the correlation to be between -1 and 1. And all that happens automatically. So you should really always call get prior before you call BRM, just to make sure what priors it's using, and give yourself an opportunity to say, well, I can come up with something better here. And you usually can come up with something better than improper uniform for these coefficients in the regression part of the model here. It's not as if being like 1 year older reduces your expected time to live under this disease by 1,000 or anything crazy like that. So you can probably do weekly informative priors on these, and it might work even better than this. But the get prior function is almost indispensable in BRM. Questions about that? Nope. Okay, so I referred to previously, class, when you're calling set prior, it defaults to be, we've seen other class things pertaining to the class of parameters, really more type of parameter. So B refers to what the regression coefficients, what I called last week the common regression coefficients, but can also be thought of in some circumstances as like population level coefficients. We talked about this when we were talking about the wage model. So there's some, for the United States as a whole, coefficient relating, years of schooling to log wages. That's sort of a US average coefficient. And then in each state, there's going to be some deviation from that US average, places where schooling is rewarded more, other places where schooling is rewarded less. So there's a variety of things you could specify for the class argument to set prior, but the most common ones and the only ones really going to worry about today are intercept, standard deviation, core, sigma for the standard deviation of the errors, and of course the default, which is B, which refers to the coefficients. That's the choice of B there is a little bit unfortunate. In econometrics, it's common for people to refer to regression coefficient estimates as B as opposed to like beta hat. But what we talked about last week, when you're using stan GLM based on the syntax that's popularized and the notation popularized by the LME4 package, they refer to the coefficients on the population level variables as beta and the coefficients on the Z matrix as B. Whereas in VRM, B matches up with what we call beta. And it's going to have, other things for these patient level intercepts that are not called B. So, different subfields use different notation. Paul is, more talking to like medical people than social sciences. So you get a little bit of differences there, but for the most part, a lot of the function names and concepts and stuff have been harmonized between VRM and RStanOrm.
So this B is not the same B as, or is it the same B as we spoke about that day?
Not the same B. So B here corresponds to what we call beta. And these patient level things, they have a different name in VRM. Okay, so after you estimate a model and using VRM, you can call the so-called hypothesis function. RStanOrm does not have an equivalent of this. In a lot of places, this is going to be kind of misleading. In the places where it's not, you can implement the thing yourself in RStanOrm by first calling as matrix. So you might want to test, although test isn't really the appropriate word, evaluate a hypothesis that this coefficient is positive. So all you need to do if you're doing this in RStanOrm is sort of generate the 4,000 draws using as matrix and then count up the proportion of those that are positive on the parameter of interest. The BRMS package kind of wraps that all up into a hypothesis function, which takes at least two arguments, X, which is the thing produced by BRM, and hypothesis, which is a string naming the hypothesis that you are trying to investigate. All this stuff in ... gets passed down to an internal function called hypothesis.brmsFit. BRMsFit is the class of the object that's produced by BRM. It's similar to the stanfit or stanreg classes of RStanOrm. But anyway, so you can specify hypothesis in a string like income greater than 0, and it will get the draws and count up the proportion that are greater than 0. So I don't want you to get too attached to this function because it's mostly intended to pertain to medical researchers who are even more indoctrinated in frequentist methods than social scientists are. And so this is sort of intended to appeal to people that sort of have a rule that you have to test a hypothesis. But it's not really testing a null hypothesis. What you're putting in is pretty much what frequentists would call an alternative hypothesis, the hypothesis you're trying to claim support for your data. Also, these, insofar as these make sense, these are going to be hypotheses involving inequalities rather than point numbers like 0. Unfortunately, the hypothesis function also allows you to specify a hypothesis in the form of like income equals 0. This doesn't really test that null hypothesis, but what it does is evaluates the ratio of the posterior density at 0 to the prior density at 0. And if that ratio is greater than 1, then it's sort of claimed that the data support that hypothesis more than the prior did. That's still something very different from testing a null hypothesis in the frequentist way, but you'll see people who are basically frequentist, but when they try to estimate their frequentist model, it doesn't go well, and so they try VRM, but they still want to use sort of the language of frequentism. Maybe they understand what they're doing, maybe they don't, but it's out there. Okay, so we're gonna do in a second an ordinal model comparing the different ways to do it. We haven't talked about ordinal models yet. They're extremely common, or there's lots of opportunities to do them in the social sciences. Pretty much most survey questions about like politics or stuff like that will take answers on an ordinal scale. So a typical thing to see is like, they'll ask you a question as to, whether you, favor or oppose like Donald Trump's plan to do, this or that thing. And there'll be like 5 choices: strongly agree, something that conveys neutrality, disagree, strongly disagree. And the respondents can choose among one of those. And so this is sort of a generalization of a Bernoulli model to the case where you have J possible answers as opposed to just 2 possible answers. But certainly in the social sciences, you'll see a lot of people who don't really know how to deal with ordinal models. So they'll just cut up the 5 categories into 2 categories. Something like, strongly agree and agree are recoded as both being 1 and everything else is recoded as 0. That loses information compared to what the survey respondent provided. And is typically not a good idea. So in these ordinal models, there's actually 2 different ways of dealing with unidentifiable parameter. In R, it's common to take out the intercept and estimate what's known as cut points, J minus 1 of them. In Stata, there's actually a different convention, but we're not going to worry too much about that. So the idea of this model is that the observed category you see, Y, takes the value of 1 if this additional unknown, let's call it Y star can be interpreted as utility. If utility is less than or equal to the gamma 1, where gamma 1 is known as the first cut point, then the model specifies, okay, the person will say 1 or whatever is the lowest category on the ordinal scale. So this might be like strongly disagree, something like that. If the person's utility for the question falls between gamma 1 and gamma 2, then the model says, okay, the person is going to choose the second lowest category, all the way up to the point where the person answers in the jth category, which often is 5, if their utility is higher than the J minus 1th cut point. And these cut points, the gammas, they're unknown, and they have to also be estimated. From a Bayesian perspective, you can think of utility as an additional unknown that also has to be estimated. But the usual way of doing this in STAN, the way RSTAN-ARM and VRM do it, they're actually integrating out the utility. So we're only estimating the cut points and then betas and things like that. So the typical way of specifying this model is to make utility a linear function of x. There's some unknown coefficients there on the x variables that you're going to have to estimate. This is only one way of specifying ordinal model. It's probably the most common one. This is sometimes called the sort of cumulative model or proportional odds model. Proportional odds really only makes sense if you're using a logistic assumption about the errors in utility. And different assumptions can be made. The two most common are to say that utility has standard normal errors. This results in a so-called ordered probit model. That can be estimated by Gibbs sampling. It usually does not work all that well. It's sort of too complicated model for Gibbs sampler to work well, even though the full conditional distributions are relatively easy to derive. You get inefficient samples, they converge slowly, they mix slowly. Your estimates based on a finite number of draws tend to be considerably off the true expectations, etc. There's also the ordered Logit model. Of course, ordered probit is more common with economists, ordered Logit more common with statisticians. Very little difference in the assumptions between those two distributions for the errors. But if you do logistically distributed errors, then there, as far as I know of, no Gibbs sampler for that case. You can't derive the full conditional distributions. All that's irrelevant from Stan's perspective. It doesn't do full conditional distributions. It just draws from the joint distribution of all the parameters. So it doesn't really care what assumption you make there, and it will tend to draw pretty well from the posterior distribution of all these parameters. All right. Some of you may have seen that before. Just to sort of restate the same thing in graphics. So here we have on the right the CDF. This is the standard normal CDF. And so it's bound between 0 and 1. And in this, you can sort of see more clearly what is, the assumption of the model. So what it's saying is, okay, if your utility for whatever it's asking about is greater than this value here, then you're in the jth category, the biggest category. If your utility is to the left of, this, then you're in the first category. If your utility is between, here and there, then you're in the third category. But the locations of these cut points, the vertical lines, has to be estimated. And so you can get like thinner or whatever intervals on which people are assumed to fall in this or that category. And the utility is a linear function of the x variables. So that can vary from person to person. We can put the same information using the standard normal density function, in which case the proportion of people in each category, if you're just estimating a model with an intercept, is given by the area between cut points, etc. But as usual, I find it easier to think about the CDF rather than the PDF, which is its derivative. So we're going to estimate where those cut points lie. The likelihood, it's pretty much a categorical likelihood or multinomial likelihood with one realization per person. So this is the function for the likelihood of the parameters. So this is both the betas and the gammas, even though I didn't write the gammas here. It's proportional to this product, the probability that Y falls in category J. But this is raised to the power Y, where now we're interpreting that Y as being like 1 or 0, depending on whether you're in the jth category or not. So for one of these, it's going to be raised to the power of 1. For the J minus 1, other of them, it's raised to the power of 0. So that's just going to be 1. And so the only probability that's active here is for the one that the person actually chose that category, in which case you have some probability there of being in category J given your X's. So F, as usual, is a CDF. Typically, it's going to be one of the ones in the location scale family. So standard, normal, standard, logistic, stuff like that. And so the probability that you are in category J or less is can be represented by evaluating the CDF at X transpose times beta plus some error term that you're making assumptions about. Is that less than or equal to the Jth cut point? And so if you use like the standard normal, that can be represented by this, by putting it into z-score units. You can, one thing that's a bit confusing here is, okay, we have this sigma, but actually when we estimate the model, an ordinal model, there is no sigma, and that's because we set it to 1, again, for identification reasons. So let me briefly explain why that is. If we multiplied everything by some positive constant A, then that would, change the shape of things, but it doesn't change the order of anything in an ordinal model. And so now we would have some CDF that's like gamma times A minus X times beta times A, and then we'd scale up sigma by A as well. All the A's cancel, and we're left with the same thing that we had before. And so that is basically telling us that the data, if it was generated by this model, cannot distinguish A from sigma. So everything can be multiplied by a positive constant without changing any of the observed implications for the model onto the data. And so to get around that problem, we fix sigma to be 1, in which case you can no longer multiply by any value of A other than 1 without changing the observable implications of the model. So even though we often make assumption that the errors are normal, we're actually making the assumption that the errors are standard normal. They have a variance of 1 to get around this problem that otherwise we would only know the parameters up to a multiplicative constant. We have to make that multiplicative constant be 1 in order to get estimates and stuff like that out of Stan. So this also comes up in binary logit and binary probit models. It's, again, not estimating a standard deviation. Now, there's an exception to this, although I don't think it's supported by VRM and it's not supported by RStanArm yet either. What if you knew what the cut points were? And that might sound a little bit weird. But a lot of times in surveys, they actually will put the cut points into the question. Like they'll ask, what is your income or whatever. And instead of writing in like a number, you're given 10 categories. And so the first is like less than or equal to 10,000. And the second is between 10,000 and 30,000 and, things like that. In which case you shouldn't be estimating the cut points. You know exactly what the cut points are. Those are data. And so if you fix the cut points, then you can't multiply the cut points by A without changing the implications of the model. In that case, you actually could estimate sigma. So that's a pretty easy model to implement in Stan, but neither RStanArm nor BRMS, as far as I know, actually have implemented that model where you fix the cut points rather than fixing sigma. All right. Any other questions about ordinal models? Okay. So you can estimate an ordinal model in both rstan_arm and V Rms. In rstan_arm, you use the stan underscore POLR function, which piggybacks on the POLR function in the mass package. The reason why it's called POLR is proportional odds logistic regression. So I think it's started out as only supporting logistic assumption about the errors, but has subsequently been generalized to make other assumptions about the errors. So if you want to assume the errors are standard normal, you can just specify method equal probit as the argument there. So this data set comes from the VRMS package, has something to do with how you would rate your asthma, I guess it is, symptoms for some sort of different treatment that they put, some difference in the inhaler, or more likely some difference in the compound in the inhaler. And we're going to specify, that it varies as a function of this treatment and what period the data were observed on, and whatever carry means. I guess whether you carry your inhaler, I don't know. Like stan underscore LM, the prior for this is specified on the R squared parameter. This is a little bit harder to do because this R squared pertains to what's the proportion and the variance of utility that can be explained by the model, rather than something on the actual observed ordinal categories that we see. In general, for a lot of these ordinal sorts of models, particularly in the social sciences, our models are not very good at explaining differences in utility, so we tend to put in low numbers here, as opposed to like what we did for diamonds or something like that. So you can estimate this model, and that's fine. And so if you wanted to estimate, the treatment variable, I assume, was assigned randomly, so we might want to estimate the causal effect of the treatment variable on, how you rate your symptoms or something like that. This is straightforward to do using the post-estimation functions, and this process works even if you're specifying a lot more, much more complicated model. So we start off by creating another data frame that's just a copy of the inhaler. And in that new data frame, we hypothetically set everybody's value of the treatment variable equal to 1. Then we generate the posterior distribution of utility for each observation if the person were treated, call that Y1 star. Then we change the treatment variable to be 0 for every person, generate their utility if they were in the control group. And then the difference between those two is what we believe to be the difference about the treatment effect. And in this case, you can see it's estimated to be about -0.5, and at least the interquartile range is pretty small, entirely negative. So apparently this treatment, I'm going to guess, reduces the severity of the symptoms. But depending on how it's coded, it might make the symptoms worse. I don't know. But it is telling you it's estimated reasonably precisely. That same estimate is available if you just print out the results, but it's phrased in terms of the posterior median here. You also get estimates of the other things, including the cut point between category 1, category 2, between category 2, category 3, etc. So we get posterior medians, posterior standard deviations, indeed posterior everything on all those. Our stan arm will also get the posterior predictive distribution for the proportion of people in each category if X were set to its sample means. So we got that. And in BRM, we can estimate a similar model. BRM has the additional feature, which is not yet built into Stan_Fuller, that you can allow the intercept to vary from one subject to the next using LME4 style syntax. BRM also has some other options that estimate a little bit different of a ordinal model. So in this, I specify family equals S ratio rather than family equal cumulative. So that's another way of looking at an ordinal model that sort of thinks, okay, people just kind of go, start at the lowest category and then kind of think up, and then they decide to stop at some point on the ordinal scale. That implies a little bit different of a likelihood function. So we could estimate those two. Here I'm specifying a prior of normal -1 standard deviation of 2 on the treatment effect. But there's also an additional thing here where I wrap treat inside the CS function. That indicates that the effect of treatment is allowed to be specific to each category. So it's going to be estimating a treatment effect, not just for utility overall, but category 2 versus category 1, category 3 versus category 2. So that can sometimes be appropriate. Whether it's appropriate or not for this data generating process is best assessed by passing the two competing models to the LU function. In this case, if you do that, you'll get warnings saying that the assumptions of the LU procedure are not really being satisfied. But if those warnings did not exist, you could compare the models on the LU information criterion, and taken at face value, it's saying the simpler model, which we estimated up here, is more likely to predict future data better than the more complicated model that we estimated second, which estimates more parameters. So you can see the output of these ones that are estimated by BRM. It's a little bit more verbose. It's estimating a larger treatment effect when it allows the intercept to vary by subject. These intercepts 1, 2, and 3, those are the cut points. So those are pretty similar to what we were estimating before. But fit 4, which is the one that relaxed some of these assumptions, it's estimating additional parameters, one for each of the J-1 categories of the output. So a specific treatment effect for 1 versus 2, 2 versus 3, etc. Those are estimated less precisely. There's less information in the data about them. And so even though this is a more flexible model, the evidence from the LU information criterion reasonably strongly suggests that the simpler model is more likely to predict future data from this data generating process better. But it could have gone either way. Okay, that's all we have time for today. We'll come back, pick it up Thursday, start to do some even more complicated models with BRM, and also emphasize the things that you need to be watching out for when you estimate some of these models. So I'll see you then. Also, mark on your calendars for Friday afternoon, the review session.